everybody. My name is Dianne Xiao, and I'm an associate professor in the Department of Chemistry at the University of Washington in Seattle. Like many other inorganic chemists, I was drawn to transition metals because of their beautiful colors, like the beautiful blue of copper sulfate crystals or the deep purple of potassium permanganate. On the top right is a photo of a demo that I do often in class and at outreach activities. The two layers in the test tube highlight how cobalt 2 plus can be dramatically different colors, either blue or red, depending on what is bound to the cobalt center and its geometry. So how does this all relate to Dr. Arnold O. Beckmann? Well, his invention, the Beckmann DU UV-Vis spectrophotometer, which he called his most impactful invention, has allowed us to go from eyeball spectroscopy, so just seeing these visually with our eyes, to actually quantifying the amount of light that transition metals absorb and at what precise wavelengths. Through this, chemists can obtain a wealth of information about the metal's identity, its oxidation state, geometry, and local environment. UV-Vis spectroscopy is now an indispensable tool for anyone studying the chemistry of transition metals, whether in the context of molecular systems, materials, or in biology. In addition to the impact of his scientific inventions, Dr. Arnold O. Beckmann, as well as Mabel Beckmann's philanthropy, has also deeply impacted my life and career trajectory. As a postdoc in 2017, I received an Arnold O. Beckmann postdoctoral fellowship, which allowed me to pursue exciting yet unfunded research directions in my postdoctoral lab. That same year, I attended my first Beckmann Symposium, which connected me with peers, mentors, and also younger trainees. I remember seeing the outstanding presentations of undergraduate Beckmann scholars and being convinced that regardless of someone's age or level of experience, they can achieve excellence in research with the right support. A few years after I started my position at the University of Washington, I received a Beckman Young Investigator Award, which gave me the resources and financial safety net to be ambitious in my lab's research directions. As I advance in my career, I'm really excited to give back to the foundation and contribute to the mentorship of younger scientists through programs such as the Beckman Mentoring Program. My research group is fascinated by porous materials and the chemistry that can happen on the surfaces and inside the voids of these confined spaces. We are a synthesis-driven group, which means we like to make things that have never been made before and study their properties. We use the entire periodic table, from organic to inorganic chemistry, to make both porous materials, so structures that extend indefinitely in 1, 2, or 3 dimensions, as well as discrete porous molecules, so things like molecular cages and macrocycles. The reason why porous materials are exciting to me is because their incredibly high internal surface areas aren't inert. Their surfaces can be functionalized with catalytic sites that can carry out chemical transformations, or binding sites that can specifically separate one molecule from another. Chemical catalysis and chemical separations enabled by porous materials, so porous catalysts and porous adsorbents, are involved in the production of nearly every commodity chemical. What my group is interested in is trying to develop new porous materials, so porous catalysts or porous adsorbents that can use renewable energy sources and renewable feedstocks to make these same chemicals that we use today. In particular, the overarching goal of my Beckman Young Investigator Award was to design new electrically conductive porous materials that can use renewable electricity to drive chemical transformations. This figure shows simplified schemes of what we're trying to do, so electrochemical synthesis, where we use electricity to reduce or oxidize a molecule, as well as electrochemical separations, where we use electricity to selectively bind and release molecules in a mixture. As you can see here, for these applications, we need surfaces that are not only electrically conductive, but also chemically tunable, so that we can design in a specific active site for catalysis or binding site for separations. Currently, the most common conductive additives used by researchers are all based on sp2 hybridized carbon. Some examples of well-defined structures that sp2 hybridized carbon can make are shown here. My BYI proposal asks the question, can we make these same types of structures with other elements on the periodic table, and can the addition of these new elements introduce reactivity or properties that are not possible with just carbon? These are some simplified representations of molecules and materials that we've synthesized, where we've installed conjugated metal organic building blocks as well as organic building blocks into porous scaffolds. As you can see, these building blocks include many more elements than just carbon. We can use these new porous materials for a variety of catalysis and separation applications, including electrochemical CO2 capture. This technology relies on redox carriers that cycle between two states, a reduced form that binds CO2 strongly and an oxidized form that binds CO2 weakly. In BYI-funded work, we've incorporated CO2 redox carriers into diverse porous macrocycles and framework structures and shown that they can be used as solid-state electrochemical adsorbents, reversibly binding and releasing CO2 over many cycles. Lastly, on this slide, I've shown a few of the other materials and molecules that we synthesized with the support of the BYI award. In addition to solid adsorbents for electrochemical CO2 capture, we've also studied redox-active cages as mediators for organic electrosynthesis. We've also developed macrocyclic molecules that stack into porous nanotubes, where the walls are not only electrically conductive, but the materials are also solution processable, enabling simpler device fabrication. Using a variety of tools, including the UV-Vis analyses that were enabled by Dr. Beckman's inventions, we've characterized the fundamental magnetic and electronic properties of our materials. Finally, none of the research described here would be possible without the support of the Arnold and Mabel Beckman Foundation. I'd like to extend a heartfelt thank you to the Foundation for supporting the people that do the research at all stages of our careers. Thank you so much for supporting young scientists.